All right, let's dive right in. Today, we're exploring the absolutely wild world of quantum materials. This is where scientists are basically acting like atomic-scale architects, trying to build the future of technology literally one atom at a time.
So, to get started, let me ask you a question that sounds like a complete paradox. What if you had a material that stops electricity dead in its tracks on the inside, but lets it flow perfectly without any resistance right on its surface? I mean, it sounds totally impossible, right? But believe it or not, this one weird property is at the very heart of a huge technological revolution.
So, let's kick off our little scientific detective story by getting to know this material of opposites. It's a substance that promises to unlock some of the most powerful, most exotic states in all of quantum physics. Okay, so the main character of our story is something called a topological insulator. Now, the best way to picture this is to think of a chocolate truffle that's wrapped in a really thin conductive foil. The chocolate on the inside, that's the insulator. No electricity is getting through that. But the foil wrapper on the outside is a perfect conductor, where electrons can just zip along like they're on a highway. It's this strange, two-faced personality that makes it so incredibly special.
And why should you care? Well, because that perfectly protected superconductive surface is the ultimate playground for all sorts of bizarre quantum effects. If we can control what happens on that surface, that's a massive step towards building stable, mind-bogglingly powerful quantum computers. So yeah, the stakes here are incredibly high.
All right, let's meet the specific materials under our microscope. What you're looking at here are the atomic blueprints for two really promising candidates in this field. Now, on paper, they look flawless. These beautiful, perfectly ordered, layered structures. They're designed to have exactly the quantum properties we want. But, as scientists very quickly found out, what you see on the blueprint isn't always what you get in reality.
And that brings us to the central conflict of our story. In this whole quest for the perfect crystal, researchers hit a snag, a really unexpected and frustrating one.
Yeah, despite their perfect design, these materials just weren't behaving the way they were supposed to. There was a critical flaw hiding somewhere deep inside their atomic structure.
And here's the problem, pretty much straight from the research paper. Instead of being these perfect insulators on the inside, they were acting like plain old metals. The whole thing was conducting electricity, and that basically short-circuited those special surface states, making them completely useless for any quantum applications. The magic? It was gone. So what was causing this massive short circuit? Well, the culprit turned out to be these tiny, almost invisible mistakes in the atomic pattern, what scientists call defects. You can think of them like typos in the material's most basic code, totally messing up the perfect pattern and changing how it behaves.
So this kicked off a full-blown atomic-level investigation. Scientists had to become detectives using these incredibly powerful supercomputer calculations to hunt down the specific defect, the one typo that was ruining their perfect material.
And guess what? They found it. The main bad guy was something called an anti-site defect. Here's what that means. In a very specific spot where a small manganese atom was supposed to be, a much bigger bismuth atom was shoving its way in and taking its place. This one single atomic swap was releasing a bunch of extra electrons, and that's what was turning the whole insulator into a mess.
Okay, let's look at the evidence. This slide shows what are called formation energy charts. All you need to know is this: the lower the line is on the chart, the more likely that specific typo is to happen. And would you look at that? That lowest red line, which is our bismuth for manganese culprit, is way, way down at the bottom. This was the smoking gun. The calculations proved this mistake wasn't just possible, it was practically guaranteed to happen all the time.
So the next question is, why was this specific typo so common? Well, kind of ironically, the material's own unique layered structure was the source of its downfall. When you sandwich all these different atomic layers together, it creates a ton of physical strain inside the crystal. And this internal tension literally stretches the spot where the little manganese atom is supposed to sit, which makes it way easier for a big bismuth atom to just pop right in. It's a fundamental flaw that's born from its own complex design. But, just identifying the problem is only half the battle. This is where our story shifts from detective work to some seriously clever engineering. Because now that the scientists knew the exact flaw, they could start figuring out how to fix it. And their calculations showed them two possible ways to get to that perfect crystal. The first was pretty passive. Just change the recipe you use to grow it. The second was much more active. Add a whole new ingredient to go in and counteract the bad guys. So solution number one was all about adjusting the chemical recipe.
It turns out, if you grow the crystal in an environment with a ton of extra tellurium, you can subtly shift the material's baseline energy level, what physicists call the Fermi level. You can think of it like fine-tuning the material's electrical idle speed, just making it less likely for those extra electrons to cause any trouble. It's kind of like changing the temperature in the oven to get a much better bake.
Now, the second solution was way more direct. It involves a process called doping, which is where you intentionally sprinkle in a few atoms of a totally different element. The goal here was to find a counteragent, an atomic antidote that could go in and neutralize the damage being done by those pesky bismuth defects.
And after running the numbers and testing a whole bunch of candidates, the calculations pointed to one single clear winner for the job: sodium.
Let's go back to the data, because these charts show exactly why sodium is the perfect antidote. Just focus on that low green line. That represents a sodium atom taking the place of a manganese atom. And because its line is so low, we know what happens really easily. But here's the crucial part. Sodium acts as an acceptor. It's an atom that loves to soak up extra electrons. So it goes in and perfectly cancels out the problem that the bismuth atoms were creating. It's a perfect fix.
And this graph right here, this is the victory lab. It shows exactly what happens. As you add more and more sodium, that's moving from left to right on the chart, watch how that red line, our energy level, gets pushed down, down, down. It moves right into that sweet spot, that energy gap that makes something an insulator instead of a conductor. The sodium is literally cleaning up all the electrical noise, transforming the flawed metal back into the perfect insulator it was always supposed to be.
So let's zoom out. What does all of this really mean for the bigger picture? I mean, this discovery is about so much more than just fixing one or two specific materials.
What we're really seeing here is the birth of a powerful new strategy, and it's called defect engineering. So instead of just treating these atomic typos as unavoidable flaws, scientists can now predict them, understand them, and even use them to their advantage, or in this case, use other elements to perfectly cancel them out. It's a completely new level of control over matter itself.
And this is why it matters so much. This isn't just some abstract lab exercise. This is a vital step toward building the kinds of materials we need for real, fault-tolerant quantum computers, the kinds of machines that could design new drugs or crack today's toughest encryption. It allows physicists to finally test some of their wildest theories about the universe. We are really entering a new era where we don't just discover materials, we design them, atom by atom, to solve our greatest challenges.
Which leaves us with one final awe-inspiring thought. We've just seen how scientists can find a material's greatest weakness and turn it into a source of strength. Now that we have the atomic toolkit to start building these perfect quantum materials pretty much on demand, the real question is, what impossible things are we going to make possible next?